Well, good morning, good afternoon, and good evening, ladies and gentlemen. It's a great honor for me to be presenting in front of you today, although virtually this time. I hope you are having a good day so far. My name is Costa, and my talk today is about using synthetic production data from an open source carbonate reservoir model to improve our understanding of flow behavior. We're using an in-house carbonate reservoir ensemble, which was built by myself under the supervision of Professor Sebastian Geiger and Professor Daniel Arnold at Reservoir University. In part one of my outline, I'll start off with the research objective, which has been to create a new open source carbonate reservoir benchmarking case study that accounts for geological uncertainties inherent to carbonate reservoirs. I'll mention briefly the existing open source models, and then I'll go straight into the ones we have developed in-house, which comprises of one undisclosed truth case, along with 72 open access geological versions for the same dataset. In part two of my talk, I'll go into the philosophy of our model construction, the synthetic petrophysical data, the reservoir rock typing technique used, flow unit architectures constructed, and finally the model initialization. This will complete the geological components of this work, so we can move on to part 3, which is the reservoir simulation with all its inputs. Synthetic production data was acquired from our truth case using a virtual drilling campaign which we designed to make it as realistic as possible. And this is for the history matching component of our work, where we want to test the performance of our 72 different geological versions against our undisclosed truth case, and then determine the impact geological uncertainty has, a particular geological uncertainty has on, for instance, flow rates, water cuts, recovery factors, and so forth. Finally, we'll conclude the talk by showcasing the total uncertainty envelope between all 72 simulation runs against our truth case and all the learnings from that. The research objective of this study is to build an ensemble of realistic carbonate reservoir models with a hierarchy of uncertainties delivered in an open source format for benchmarking, upscaling, history matching, optimization, numerical method development exercises, and potential tutorials and senior design projects. Because if you're in the industry or you're in academia and you're looking to develop new numerical algorithms for reservoir characterization, reservoir simulation, what have you, you first need to have a subsurface type analog model to test your specific objective functions. A lot of people use open source reservoir models because they're easy to come by, and fortunately they are there because to acquire geological models from an operation company, international operation company for instance, they're very hard to come by, and if you were to acquire one, you would face confidentiality issues. So using open source reservoir models has played a huge advantage in our industry. A lot of new algorithms, a lot of new techniques, modeling techniques have been created based on some models that institutes and professors alike have created. To name a few, we have the Punk S3, SPE10, the Bruges field, the Stanford 6, Watt field, and Unisim 11, just to name a few. And most of them, all of them except for Unisim, are depicting of siliciclastic sediments, deltaic coastal environments, meandering channels, and so forth. The first initiative to create a carbonate reservoir model was that by Unisim. That was recently in 2015. Out of all that exists currently, the first initiative to account for geological uncertainty in reservoir modeling building was that known as the Watt field. So you have multiple geological versions for the same data set by interpreting, let's say, the formation tops differently, the fault locations, and the petrophysical properties, just to name a few. So what we've gone out to do is essentially that, but for carbonate reservoirs, because carbonates also have unique carbonate geological uncertainties, and when it comes to characterizing and modeling them. On this slide, I will explain some of the major carbonate reservoir uncertainties we have incorporated in our modeling and interpretation of the dataset. Starting with the figure on the left, with y-axis is the carbonate reservoir uncertainties, accompanied by x-axis, which shows the different model scenarios. At the top, we have our truth case, which is a very high-resolution geological model, which I'll explain in the next slides how we constructed it. It has its own unique STOIP, oil, water, gas rates, along with pressure. I have then rebuilt with the same data set using a different concept of the subsurface via the stratigraphic framework starting. Then we have the reservoir rock typing technique, the diagenetic overprint, and formation wettability. These are just to name a few of the large-scale geological uncertainties that one has to decide and interpret when modeling reservoirs. On the right, We also have the reservoir modeling and decisions to make, all of which can have an ultimate outcome when building models, be it which attribute, approaches, techniques, drivers, and methods one is to use. Modeling this stochastically, deterministically, facies-driven, non-facies-driven, and so forth. The research outcome and releases of this work is to deliver 72 geological versions of the truth case, which account for a large range of hierarchical, geological, interpretational, and modeling uncertainties. It comes with synthetic logs, so you can rebuild your own geological models, along with the related literature paper references, which is over 200 papers of the Middle Eastern Upper Karaib member, which we have tackled in this work as an analog reservoir. Synthetic production data will be released, which is part of the history matching aspect of this work, along with the synthetic SCAL database, which I will talk about in the next slide. And all of this is now in Q4 2020. So let's look at the figures now. We have multiple rock type scenarios. So we have a full-blown 27 rock type model showed at the bottom, followed by a 7 rock type version, 5 and 3. Of course, the poroperm transforms. The free water level uncertainty, we have roughly 30, we've incorporated a 30-foot geological uncertainty in the free water. And the stratigraphic framework, we've currently built 2 geological ensembles, be it I've interpreted the formation tops slightly differently. The baffles, the location of the baffles, for instance, to change the KVKH, and so forth. To create a case study, it was extremely important that it be inspired by real data and reservoir dynamics, but entirely synthetic so that we can release the data set and the models. So where was I going to get inspired to create such a case study? Well, having lived, worked, and studied in the United Arab Emirates, it felt appropriate to continue studying the carbonate reservoirs of the region. On the left-hand side image, we have the Middle Eastern region with the Jurassic oil field map. And highlighted in red is the area of interest, the United Arab Emirates, more specifically the Bab Basin. In the Bab Basin, there's one geological formation known as the Upper Karaib member. It's extremely prolific and is found current day onshore and current day offshore the United Arab Emirates. The height difference between current day onshore and current day offshore is about 3,000 foot. So the same geological formation is found and has been pushed down due to the subsidence of the Arabian Plate. And that's shown in the center image where we have a cross-section of the field, or the reservoir, geological formation, highlighted in red. The philosophy of our work was to try to capture the large-scale geological features of the region for the same geological formation, be it from platform to basin, into one single model, without all that subsurface Himalaya-like structure. So the first task was to try to reconstruct the entire region in a miniaturized version, and also with a common free water level, so that we can then look at the dynamic behavior of platform to basin into one single model. This model is entirely synthetic. We therefore did not use any seismic data to construct it. On the contrary, we started with contour maps. So I literally sketched the reservoir. I wanted to have initially 2 anticlines so that we could also look at the uncertainty and spill points, compartmentalization, and so forth. But essentially to have one anticline capture the platform interior, platform margin characteristics, and the other more of the outer shelf, basin characteristics. We then have multiple uncertainties in the aspect that I wanted to incorporate, be it the sequence boundaries, the internal flow architecture, KV-KH ratios, and so forth. So in this slide, I'll finally show you the actual model. It is the petrophysical models, the facies, saturations, the synthetic contour map highlighted in the top left, and the characteristics generally between the shelf, platform, transition, and basins that we try to capture from the region into one single model with a common free water. To do this, several wells from multiple fields in UAE were from different geodepositional positions and height above free waters were used. Basically, we synthesized open hole logs that we try to mimic realistic reservoir characteristics that we find in literature and in gray sheets, and core data as well. So everything had to be inspired by real logs and publications, and the facies and diagenetic overprints as well from literature. We try to capture the general heterogeneity is found in and around the basin for this specific reservoir. All the data has been anomalized, rescaled, repositioned, and structurally deformed, so the free water levels were normalized, and the entire model was placed in a unique coordinate system. So here is on the right is the final petrophysical models. Here we have the density, porosity, and permeability showed here. Porosities and densities, if you look on the top left-hand side platform area, you start to see these lower density values. We can consider that siliciclastic deposits coming from the shelf to the platform. We also have permeability contrast, which is typically known for the region to have almost a 1 order of magnitude difference in permeability from B upper to B lower, and causing contrasts. This contrast in permeability of such can have impacts on, for instance, waterfronts, water floods, reverse water coning, and this is things that we have to try to honor and capture in our model. Continuing on, showing you here, top right is the Winland R35. So we have modeled the pore throat size distribution generally, capturing large pore throat size depicting of grain-supported limestone fabrics in the topmost part of the reservoir, mainly in the platform and basin, and mud-supported limestone fabrics with smaller pore throat sizes in the base of the reservoir. And this is typical characteristics of the region for this upper chloride member. That was one of our anchoring points for our facies rock types distribution, to link pore throat size distributions with a specific cap curve and an irreducible water saturation value. And then from there, we initialized the model. So this is our true saturation with height above free water. And this is built as an undersaturated model with multiple production development scenarios to be played with. Now it shows, if you bottom left of the image, we have the saturation. It shows very realistic fluid distributions with height above free water. So many carbonates, they have very thick capillary transition zones because carbonates can tend to have lower permeability values than, for instance, siliciclastic sediments, not to mention shales. But essentially we have captured, for instance, multiple oil-water contacts and very thick capillary transition zones. When it comes to saturation height modeling, there's a lot of uncertainties there. When it comes to our model, we have used a Skelt-Harrison saturation height functions. Before doing that, we then need to group our porosity permeability distributions in 3D space and propagate them so that they're interlinked, be it a bivariant sequential Gaussian simulation, which is what we've done. So we have used Winland. We have 27 Winland pore throat size ranges, which is those transforms in the center. And then we did a sequential Gaussian simulation of porosity linked with permeability linked with the porosity in 3D space. For each saturation, for each rock type, there's a saturation height function was developed. Of course, there are many different methodologies that one could use, be it J functions, Omer functions, Tournier hyperboles. Some are better for unimodal, bimodal, and trimodal distributions, which is unique in carbonates. Sometimes you have these trimodal distributions, and you should apply a proper saturation height function. Nonetheless, to prove that our saturation with height is matching the open hole logs from typical characteristics found in the literature at different heights above free water, is to show you the 8 different wells here. Each well has 3 tracks. The first is the height above free water, the second is the rock types, and the third is the continuous black line is the saturation from the log, and the upscaled cells is the saturation from our functions. What this shows is that we have a very good match between saturation log and the core and the saturation functions at different heights above free water. What this also shows is that because this is a synthetic case study and we don't have MDT, even though I can synthesize that, there's about a 30-foot uncertainty in the free water. So even if I to drop or shifted the free water down or up by 30 feet, the saturation of the wells up in the structure don't vary significantly. It's more the wells down structure near the free water. But nonetheless, that's a geological uncertainty that we have incorporated in our reservoir model releases. When it comes to reservoir simulation, there's many geological uncertainties there, which we have incorporated, be it the wettability, the transition zone height and volume, and also the irreducible water saturation and residual oil saturation after water flood cutoffs. When we designed this reservoir, we wanted to make it as realistic as possible. Therefore, we had 27 rock types. We didn't want to downscale that, so we kept and constructed 27 capillary pressure curves, 27 relative permeability curves, and 27 forced inhibition capillary pressure curves to give us that realistic reservoir dynamic behavior encompassing multiple wettability characteristics, be it from water wet all the way to oil wet. The justification for giving a rock type more oil wet or water wet characteristics essentially came from the synthetic relationship. We decided to make a decision, be it any sample that had a higher irreducible water saturation value, we would assume to be more water wet, and a sample that had less irreducible water saturation, we would assume that to be more oil wet. And that's how we've gone about the synthetic relationship shown at the bottom here between irreducible water saturation and residual oil saturation after water flood. Nonetheless, everything is geologically consistent, so all the endpoints of the primary drainage and forced inhibition with the rel perm, everything is consistent in such a way to make as realistic flow behavior as possible. On the right-hand side is the multiple flow unit architecture characteristics. So, as I had mentioned to you, we are trying to capture the large-scale geological features of the region for the upper Carite member. And we've done so by trying to capture the multiple flow unit architectures when we plot with TVD sub C the normalized cumulative flow capacity in red and the normalized cumulative storage capacity in blue. You can see that there's multiple flow unit architectures, be it from platform to basin, generally speaking. The topmost part of the reservoir tends to have most of the flow, depicted here in the first one, and about 80% of the flow in the topmost part of the reservoir, about 20% in the base. That's not so true in the transitional part of the reservoir, but nonetheless, it's been modeled that way. Highlighted in red is the area we targeted first to generate the synthetic production data. So what we did is I cropped this part of the reservoir to start doing our field development plan, which I'll show you next slide. We generated synthetic production data for history matching purposes. That cropped reservoir section was initially used for the full field development plan, where a virtual drilling campaign of 18 years was designed. This cropped section is still quite large. It's still 60 kilometers long by 26 kilometers wide. The flanks are dipping 0.6 degrees in the north and south and 1 degree in the western eastern regions. We did not upscale the geology, so it's still very high resolution. It's 15 geological zones subdivided into 62 layers. The layering varies between 0.6 of a foot to 8 feet thick, and all the cells are 250 by 250 meters long, giving it a total of 1.7 active million grid blocks. We included an active aquifer using carded tracing, and now I'll start to show you over the next couple slides our virtual drilling campaign, which starts off in year 2020, where we have 17 appraisal wells, showing you in the bottom left the oil potential, 2 maps, top layer 1 and bottom layer 62, with those 17 appraisal wells and the free water level. From there, after the first 5 years, we were trying to produce, we're looking at the dynamic behavior from those appraisal wells. 10 of those are in the oil producing zones and 7 are at or near the free water level. And then we started a drilling campaign of 18 years where we drilled 206 wells, production wells, 74 infill water injectors, and 88 peripheral water injections, which I will show you in the next couple slides. On the top right hand side, we have the oil rates and water injection rates, showing you different multiple oil plateau scenarios. And at the bottom right, we have the cumulative oil and oil recovery percentages for these different scenarios. The first 5 years, highlighted here in the arrow, are just for the appraisal phase, and that's when we start drilling, our virtual drilling campaign starts. So showing you in the oil potential maps, we have 2 rigs, so we have 2 dedicated rigs, one dedicated for drilling a 5-spot vertical pattern, and the other rig dedicated to drilling peripheral water injectors because the reservoir is so large. We now have our synthetic production data for our truth case. We also have 72 geological versions for the same data set. We now want to look at what is the uncertainty envelope between the 72 model releases with our undisclosed truth case. On the bottom left, we have a series of figures, starting off with the top with the oil production rates of the 72 different geological versions, having a total range of around 25% in oil production rate. 25% in oil production rate is around, in this case, 40,000 barrels. So 40,000 barrels at today's oil price is roughly $1.7 million difference between how much you would produce daily if you were to use one model over the other. In terms of oil production cumulative, there's around a 17% difference between all the models. In terms of the field water cut, there's about a 20% difference, and recovery factor about 10%. So we have one data set, but multiple geological concepts, multiple geological modeling approaches, all of which give us this huge uncertainty envelope that is typical of reservoirs. On the top, in the center top, we have which permeability upscaling method should one use. Now there are harmonic, arithmetic, and geometric permeability upscaling techniques, all of which have ultimately give you a different distribution in terms of your pore perm transforms. In this case, I'm showing you the reservoir rock types and how they're influenced by the upscaling permeability technique that was used. Not only that, but we also have porosity from core, porosity from log. In this case study, we used both chord porosity and chord permeability. So we have 100% control in both of those aspects. However, they're modeled independently, and chord porosity tend to overestimate the porosity in a given rock unless you correct it for its overburden pressures. Logs, on the other hand, they tend to take a very large area, so they tend to average the porosity for a given reservoir unit. Therefore, which porosity should one use? We also have those versions. We have models that were built with log porosity or chord porosity. How about how many rock types are enough? Is 3, 5, or even 7 rock types enough to try to get a match between our true 27 rock types? So we have then created 7, 5, and 3 rock type versions of every single geological version that is to be released. All of it in the effort to see its impact in production behavior. And ultimately, the local grid refinement effect. As I had mentioned, this reservoir is very large, but you can even make it larger by reducing the grid sizes in X and Y. In this case, we have 250 meter by 250 meters, but if you were to use 125 by 125 or 62.5 by 62.5, you then increase your reservoir from roughly 1.7 million to 22.6 million grid blocks. And what's the impact it has on well, production rates, water cuts is actually quite remarkable, and it's good for learning purposes. Because the reservoir is so large, by reducing the grid sizes, you now reduce the numerical dispersion. And in this particular case, if you go from 1.7 to 22.2 million grid blocks, you increase the plateau by about 4 years. And therefore, all of these models, and these are just preliminary results currently to show the uncertainty envelope, but all of these models will hopefully aid our industry in many aspects. So I'd like to thank you all very much for your attention. I hope that the research objectives and message of this work is clear, and that it's hopefully will aid our industry in many areas, be it from reservoir characterization, reservoir simulation, optimization, history matching, and even machine learning. So I'd like to thank ultimately Energy Simulation for funding this work, and I'll open the floor for questions. Thank you.